Mr. B. Dhanasega is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We have the subject compiler design. We have the topic called the derivations. So, we started with the previous session at as syntax analyzer, which is otherwise called as the parser, and the parser is actually doing the syntax analysis, that is syntax verification of the source program. So, for the verification of the syntax of the source program, it uses the grammar, and the grammar has 4 components: the terminals, the variable set or the non-terminal set, then the start symbol of the grammar, then followed by the list of production rules. So, the production rules are the very important component of any grammar, as they are telling us how the various strings are all generated from the grammar. So, just we are having production rule means when you are looking at the productions, that is we will be having the left hand side and the right hand side. As far as left hand side is concerned, we are having a single variable, and the right hand side is concerned, we can have the combination of variables and terminals any number of times. So, now what is the reason for having this rule, or we call it as rewriting rules? The production rules are otherwise called as rewriting rules. The reason for having this is whenever we find A on the derivation, that is when you are recognizing the pattern, it can be expanded to its corresponding right hand side in the case of a top down parser, and in the case of a bottom up parser, whenever you find the right hand side somewhere on your stack, it will be reduced to its left hand side. So, both cases are possible with respect to whether the parser is a top down parser or a bottom up parser. So, if it is a top down parser, the left hand side is expanded to its corresponding right hand side, and if it is a bottom up parser, the right hand side will be reduced to the left hand side. But in all these, we have a component called derivation. So, one string derives another string, or one sentence derives another sentence, provided there are variables or the non-terminals available in the sentence. We call it as sentential forms, that is one sentential form deriving another sentential form. So, this derivation is actually the outcome of the application of various production rules or rewriting rules available in the grammar. So, what happens here is, you take any sentential form which will be having both variables and terminal combination, or exclusively variable combination, but not as terminal alone case. If it is a terminal alone case, then we must stop there, because there is no further expansion of the sentence. But if you have the combination of variables and terminals, or non-terminals and terminals, then every non-terminal must be expanded by using the appropriate right hand side of the rule, so that we will be able to find out the exact yield of the parse tree or exact the string to be derived. So, that is the reason why we introduce the concept called derivation into the that is parsing process. So, we call the productions as rewriting rules, and what happens in each step is, one variable is replaced by using the corresponding right hand side of the variable. Now, there are two classes of two types of derivations. One is called the leftmost derivation, and another one is called the rightmost derivation. So, now look at this particular that is a derivation here. It is an example of derivation. So, we have a grammar here. So, E is deriving plus EE or star EE or X or Y. That is, any prefix expression is an operator followed by two prefix expressions. In the case of plus is a binary, and here once again star followed by two prefix expressions, or it can be an identifier x or can be an identifier called y. So, now we have an expression which is a prefix expression which is plus star x y x. So, its equivalent the infix expression is going to be something like we are having x multiplied by y plus x, that is the meaning of that is the equivalent infix expression. We need not bother about the infix equivalent of that, but here we are trying to find out how this string is derived from the grammar. So, we have the start symbol of the grammar, it is nothing but your e. Because of the first symbol available in the string is a plus, and also we have the information that every right hand side starts with a terminal, we can deterministically select which production is to be used first. Since we start the string is starting with a plus, we must go for the first production, that is plus e. We can't start with asterisk, or we can't even start with x or y. So, we go for expanding e by plus e. So, it is done, and we have now more information about how the derivation proceeds, because the first symbol is already derived. The next symbol is going to be star, and we are very sure that the next production to be used for expanding the first e available on the right hand side of this derivation or in this current sentential form is asterisk followed by e. If I start with once again with plus, then it will generate the second plus, which is totally not needed as far as this particular string is concerned, and we can't go for x or y because we definitely wanted to have an asterisk. So, we will go for star e. So, plus star has come, and this e has the expansion with the two different e's. So, e, and these are called actually the sentential forms. So, now there is a point here we have to remember, actually there are two number of e's available, both are eligible for expansion. Either you can start with the expansion of the first e or you can start with the expansion of the second e, but here we have selected only the leftmost e. Even though both e's are eligible for expansion, we have selected only the leftmost e. This is getting expanded to star e. But if I select the rightmost e expanded for expansion, then the resulting sentential form is going to be plus followed by e followed by star e. Since we have taken only the leftmost, that is e for its expansion, we have a string or we have a sentential form plus star e and followed by another e. Now, we are having the sentential form of the form a stream of terminals followed by non-terminals. So, now we can go for expanding this first e by x because it is needed. In the next step, the second e by y, that is what we wanted to have from the input, and last one once again this e is going to be expanded by x. So, you will be having plus star x y x, which is considered as the yield as far as this particular derivation is concerned. The derivation starts with the start symbol of the grammar, that is nothing but e, and the derivation is having some number of sentential forms plus e plus star e, and finally we have plus star x y x, which is going to be the yield of this derivation. So, now we can learn about the leftmost derivation and the rightmost derivation. So, in general a derivation has to start from the starting symbol of the grammar, and it will continue with the expansion of the variables available in the grammar or in the sentential form with the appropriate right hand side of the productions, respective productions, until we find a sentential form which contains exactly terminals only. That is what the functioning of a derivation is concerned. And when you look at the language of the grammar, we have to find out the set of all possible derivations which will be giving you the set of all possible strings. So, if you collect the entire set of all strings available in the language of the grammar or entire possible set of strings of the grammar, we call it as the language of the grammar. Here we have seen the derivation, and derivations are used for deriving strings, and the strings will give you the language of the grammar, and these derivations can be either that is leftmost derivation, or it can even be the rightmost derivation also. In every step of the derivation, that is in each step of the derivation, if the leftmost variable is selected for expansion without bothering about how many number of variables are there, or how many number of non terminals are there, and how many number of terminals are there, that is if you are always selecting the leftmost non terminal for all the steps, then the derivation will be considered as the leftmost derivation. But if you do it in the reverse, in each step of the derivation, suppose if you find or if you select only the variable which is on the rightmost position, then the derivation is called rightmost derivation. So, we can have the derivations either completely leftmost or completely rightmost, but there is no point in having the mixture of both leftmost derivation as well as the rightmost derivation. It is because of there are different applications for the kind of derivations. As far as leftmost derivation is concerned, it is used by the top down parsers, and as far as the rightmost derivations are concerned, they are actually used by the bottom up parsers. So, especially when you are looking at the shift reduce parser, it is constructing the rightmost derivation, and finally it does the parsing in the reverse order, so that the tree will be constructed in the bottom up manner. But whereas when you go for the top down parsers like the predictive parser or even the recursive descent parser, it is always constructing the leftmost derivation and find out the tree in the top down manner. So, either we should go up with go on with the leftmost derivation, or we should go with the rightmost derivation, but no question of having the combination of leftmost derivation as well as the rightmost derivation in a mixed manner. So, now when you are looking at the leftmost derivation of definition or the general syntax, we will be having, that is in each step the leftmost variable is identified and expanded by the appropriate right hand side. There may be a chance for having more number of right hand sides, but for the current context, which right hand side is desired, that will be selected from the list of right hand sides for the particular variable or the non terminal. If it is the case, then we will be calling it as leftmost derivation. The general format is, so we have the start symbol of the grammar S, and after some number of steps, that is called the closure, after some number of steps we have a sentential form which is of the form W followed by A followed by alpha, where W contains only terminals and A contains, sorry, A is a single variable or a non terminal, and alpha contains the combination of variables and terminals any number of times, and it immediately generates the next sentential form which is going to be W followed by beta followed by alpha. So, what happens here is, in the place of this A we have a beta. This is possible just because of we have a production rule called A derives beta. So, whenever we find A on the sentential form which is going to be leftmost non terminal, with the help of a production A derives beta, you expand A by beta and thus giving you the next sentential form called W, that is beta alpha, where A derives beta is a production and W contains only terminals, alpha and beta belongs to V union T any number of times. So, that is what the general format of the leftmost derivation. That is, the condition is always we must expand the leftmost variable, and if you are continuously that is expanding the leftmost variable, we will be having patterns only of the form a stream of terminals followed by the combination of variables and terminals. That is what we say, that it is W followed by A followed by alpha, and later, that is after expanding A by beta, we will be having W followed by beta followed by alpha, and in this beta also there may be a chance for having some terminals, it will be combined or concatenated with W to form the stream of symbols, and then we will be exposing the next variable that will be once again eligible for expansion. So, that is about how we are finding the leftmost derivation. So, we shall continue this lecture after a short break. Welcome back. We have seen how the leftmost derivations are generated, and now we have another type of derivation, that is called the rightmost derivation. So, here the difference is, in the case of leftmost derivation always the leftmost variable gets expanded, but in the rightmost derivation always the rightmost variable is to be selected for expansion. So, now when you look at the this general structure for your rightmost derivation, so here we have yes, once again the start symbol of the grammar. So, after some number of steps we have a sentential form, that is nothing but alpha followed by A followed by W, which in the immediate next step gives us alpha followed by beta followed by W, where A derives beta is a production. See, the difference here is, where is W? But what is W? It is W contains only terminals because of this condition. And now where is W? W is actually following A, which means there is no point in saying that there is a variable or there is a non-terminal available next to this A. So, certainly this A is the rightmost non-terminal. So, this A gets exposed and we will go for expanding this. Remember that we may have more variables or non-terminals in alpha also, but we do not go for expanding or selecting those variables from this alpha. We will go for the only one which is on the rightmost position of the NAS initial form and apply the production rule, that is A derives beta. So, we will be having alpha beta W, and now whatever be the terminals on the rightmost side of this beta, they will be combined with this W to get more terminals on the right hand side, that is rightmost position, and once again we will find out what is going to rightmost variable from beta, that will be further expanded. So, the constraints here, A is deriving beta is a production and W contains only terminals, alpha and beta actually they are from variables or terminals any number of times. So, that is about a rightmost derivation. And next we are having another, that is data structure, we call it as the parse tree. So, which is going to be the output of that is your parser. So, every parser or a syntax analyzer is supposed to construct a parse tree for a valid syntactic construct, and the parse tree construction it will make use of the grammar. Actually, we will be transforming the grammar into a parser. The parser will take care of the construction of the parse tree for successful statements or that is error free statements, and when there exists an error, then automatically the construction of the parse tree will fail, saying that there is an error, or we will say that no as the message, the parse tree construction failed. So, now to look at the definition of the parse tree. So, we should know that the parse tree is an equivalent or graphical representation of the derivation only. If you think about derivation, it starts from the start symbol of the grammar and it grows in a hierarchical manner, and when you explore all branches, they are all supposed to be terminated with the terminals only, and once you find all the branches are terminated with terminal, then the parse tree construction has been successful. So, to construct this parse tree, we will use the various production rules available in the grammar, just like how we are using the production rules for the construction of the derivation, we use the production rules for the construction of the there is a parse tree also. So, this tree consists of there is internal nodes and external nodes, or the internal nodes and the terminal nodes, and what do we have in the internal nodes and what do we have in the terminal nodes. So, that will form the definition of your parse tree. So, it is going to have a root, and the root consists of the start symbol of the grammar, which is nothing but your S, that is the start symbol of the grammar, and every interior node is labeled by a non-terminal or a variable, because we call it as interior node since there is further expansion for that. Since there is a further expansion, definitely the label on that node must be a non-terminal, because they can only be expanded, but not a terminal. And as far as leaf nodes are concerned, they are labeled with the terminals or empty symbol, because they cannot be further expanded. So, that is the meaning of a leaf node. So, when you are constructing a derivation, once you have obtained a terminal, then that will be immediately considered as a leaf node, because no further expansion is possible. And as far as the interior node is concerned, if there is a label for the interior node called A, and if its children are labeled with x1, x2, x3, etc. up to xk, the meaning is, that is, this situation is possible only if there is a production of the form A derives x1, x2, etc. up to xk. So, this is actually the crux of the formation of your parse trees. That is, you take there is intermediate node, and especially with the top down parses, an intermediate node, if it is labeled with a variable, it must be expanded with the corresponding children or child node, and what will be the labels available on the child node. You just take the right hand side of the variable which is labeled on the internal node or non-terminal node, and every symbol available in the right hand side of that particular variable in the production will be given as a label for its children from left to right. So, for example, if there is a production rule A derives B, C, D, then A will be on the internal node and its children are going to be labeled with B as the label for the first child, C as the label for the second child, and D as the label for the third child. And suppose if B, C, D, they are all once again non-terminals, they will in turn be expanded to further there is stages based on the availability of productions. So, if B, C, D are terminals, then they will be treated as leaf nodes there itself with the label B for the first child and C for the second child and D for the third child. So, there is no further expansion for us, as they are already leaf nodes, no question of having further expansion. So, depending upon the label available, the expansion will be done. So, once we find all nodes are labeled with terminals, then we can say that the parse tree construction has been successfully done. Once you collect all the leaf nodes, we will be having the yield of the parse tree, and the yield of the parse tree is the string actually generated out of this parse tree or generated out of the equivalent derivation. So, that is what the meaning of the parse tree here. We have an example here. The grammar being taken as an expression is expression plus another expression, or expression multiplied by another expression, or an expression inside bracket, or simply an ID. So, this is general grammar meant for arithmetic expression. Because of this grammar has ambiguity, it is possible to have multiple derivations or multiple parse trees for sentences most of the time. So, the sentence which you have taken here is the ID plus ID star ID, that is one arithmetic plus and followed by the multiplication, and since we are knowing the priority and associativity of the operators, we will be able to come up with a correct parse tree for this sentence. But if you are not sure about the priority and associativity, then multiple trees will be produced, multiple parse trees will be produced as outcome, and from that we have to select the correct parse tree once you know the parse trees, the priority and associativity. As far as this expression is concerned, that is your ID plus ID star ID is concerned, the second ID star, the third ID will be computed first. So, we will have the parse tree like this. E is the root and which gets expanded to E plus E. Actually, this is a tree whose branches must be like this only. We have construct, that is, the diagram has been drawn with the help of hierarchical chart, but do not see it as a hierarchical chart, it is a tree where this E has been expanded to E plus another E. So, that is the first one. In the second step, we find that this first E has been expanded to ID and the second E has been expanded to E star E, as it is going to be the expression we wanted to have, and the second E now is expanded to ID and finally this E is also expanded to ID. So, we will be having this, just to collect the leaf nodes, we will be having all these colored nodes. So, ID plus ID star ID. So, that will give you the entire yield of the parse tree, and from the parse tree certainly we will not be able to differentiate whether this parse tree has come out as an outcome of leftmost derivation or the outcome of the rightmost derivation. And once even constructed, as after completion of the parse tree also, we will not be able to know whether the tree has been constructed in a bottom up approach or even the top down approach. But when we are constructing that, we know that is how the things are happening. If you are always collecting the leaf nodes and proceeding towards the root, then it will be a bottom up approach, or if you are expanding the variables every time towards down, then it will be called a top down approach. So, that is about how the parse tree is constructed. So, now look at the definition of the grammar, that is language of the grammar. It is going to be set of all strings, but the condition is for every string that is W, there should be a derivation from the start symbol of the grammar with any number of steps. We want to have that string and W must be containing only T star. That is, the string which you have obtained should contain only terminals, but not the variables or the non terminals. So, this symbol means that this derivation is from the grammar called G and it is producing this W in any number of steps. So, it is deriving this string in any number of steps, that is the meaning of this notation, derives. So, in general, if you are looking at the that is string, it should be derived from the start symbol of the grammar, then we can claim that the string is there in the language of the grammar. So, to summarize, we have seen the derivations and parse trees, that is how the graphical representation of derivations are given, and finally, we have seen the language of the grammar. So, the language of the grammar should be exactly same as the set of all strings which we want to generate from this to form the programming language, that is your programs. See, for example, if you are having a grammar for the if statement, the language of that particular grammar should be the set of all possible if statements. If you have the grammar for assignment statement, then the language is going to be set of all assignment statements. So, that is what the meaning of your language of the grammar. So, to look into the questions, the need for derivations, what is the meaning of leftmost derivation and what is the meaning of rightmost derivation, the definition of parse tree, how the parse trees are constructed for strings or sentences, and finally, it is going to be what is the definition of the language of the grammar. It is going to set of all strings from the start symbol of the grammar having derivations for those strings. So, with this I complete this episode. Thank you all.